A brilliant flash erupts on the lunar surface, brighter than Venus, brighter than any star. For a moment, the dark side of the moon glows with terrible power. If a nuclear bomb exploded on the moon tonight, Earth would witness this cosmic flash. But what if that explosion triggered a chain reaction we never saw coming? This isn't just Cold War fiction. Advanced physics modeling reveals that a modern thermonuclear weapon could launch parts of the moon into Earth-crossing orbit. The debris wouldn't just float harmlessly. It would become a cloud of lunar shrapnel traveling at orbital velocities. What really happens when we detonate the most powerful weapon we've ever built in a place with no air, no wind, and no protection? The answer will change how you look at the night sky forever. Unseen consequences. In the vacuum of space, a nuclear explosion behaves nothing like it does on Earth. Without an atmosphere to absorb energy, the full force transfers directly into the lunar surface. The most alarming possibility: debris from a megaton-level explosion could exceed lunar escape velocity. That's 2.38 kilometers per second. At this speed, lunar material breaks free from the moon's gravity. Scientists calculate that a 100 megaton bomb could eject up to 1 million kilograms of debris into space. That's equivalent to launching 6 fully loaded Boeing 747s directly from the lunar surface. Here's what most analyses miss. This material wouldn't just float away harmlessly. Some would enter unstable orbits that intersect Earth's orbital paths months or even years later, creating a silent, invisible threat to our satellite networks. Unlike meteor showers which burn up in our atmosphere, these lunar fragments would arrive with no warning. They would travel too fast for current detection systems to provide adequate alerts to satellite operators. Let's break this down. You're not just throwing rocks into space, you're creating high-velocity shrapnel. Think of it like this. Instead of bullets, the moon throws boulders, and they don't stop. When you fire a gun on Earth, the bullet eventually falls. In space, these lunar fragments keep going until they hit something. And with thousands of satellites orbiting Earth, including our GPS network and communications systems, that something could be the technology we depend on daily. What makes this particularly concerning is the unpredictable trajectory pattern. Unlike controlled debris, these fragments would follow chaotic orbital paths, making them nearly impossible to track reliably. Military detection. Chains. In the silent void of space, light and radiation travel unimpeded. A nuclear flash on the moon wouldn't just be visible to amateur astronomers. It would trigger military detection systems worldwide. NORAD's space-based infrared system, SBIR's satellites constantly scan for the thermal signatures of missile launches and nuclear detonations. These advanced sensors can detect a match being struck from geosynchronous orbit. If someone detonates a bomb on the moon, it's not private. Dozens of countries would see it instantly. Russia's OCO early warning system, China's Jianbing satellites, and the European Space Agency's monitoring stations would all record the event simultaneously. The nuclear flash would register across multiple wavelengths: visible light, infrared, gamma, and X-rays, creating a unique signature that military systems are specifically programmed to identify. But here's the twist. AI classifiers analyzing the data might mistake the event for an Earth-based nuclear launch. Modern detection systems use machine learning algorithms to distinguish between natural phenomena and weapons. These systems have never encountered a lunar nuclear explosion. The radiation profile coming from the direction of the moon could trigger false positives in automated threat assessment protocols. But what happens when military AI spots the flash and thinks it's under attack? With decision times measured in minutes, a misinterpreted lunar explosion could spark a dangerous escalation chain. Military commanders would face unprecedented pressure while verifying what their systems are telling them. If you're into these deeper, hidden layers of science and strategy, subscribe now. We break down the stuff others skip, from orbital mechanics to military response protocols that shape our world behind the scenes. Earth's response systems. When nuclear explosions occur in space, they create a distinct electromagnetic pulse that propagates across vast distances. Earth's global monitoring network would detect this pulse within 1.3 seconds, the time it takes light to travel from the moon. Defense systems in Russia, China, and the United States maintain constant readiness to respond to nuclear threats. A mysterious explosion near Earth would force these systems into heightened alert status. Missile command networks could be forced to go to high alert, even if nothing is aimed at Earth. The 1995 Black Brant incident shows how real this danger is. Norway launched a scientific rocket, and Russia briefly prepared for nuclear retaliation. This isn't science fiction. In 1962, the Starfish Prime nuclear test detonated 250 miles above the Pacific Ocean. The resulting electromagnetic pulse knocked out streetlights in Hawaii and disabled satellites 400 miles away. The explosion created an artificial radiation belt that lingered for months, eventually destroying 1/3 of all satellites in low Earth orbit at the time. A lunar nuclear explosion would emit gamma rays and neutrons that could damage unshielded electronics on satellites facing the moon. The International Space Station, with its human crew, would need to implement emergency radiation protocols. And that's just what we've seen before. But what if the real danger isn't the blast, but what it exposes under the moon's surface? Seismic revelations. A nuclear explosion on the moon wouldn't just create a crater, it would send powerful seismic waves propagating through the entire lunar body. Unlike Earth's complex geology with tectonic plates and magma flows, the moon's simpler structure allows seismic waves to travel farther with less distortion. During the Apollo missions, astronauts placed seismometers that detected moonquakes and impacts. These instruments revealed that lunar seismic waves continue for hours, not minutes like on Earth. The moon rings like a bell when struck. Now imagine the bell-ringing effect of a nuclear explosion. The blast would generate waves reaching deep into the lunar mantle, potentially providing unprecedented data about the moon's core. Modern quantum sensors could revolutionize what we learn from this violent probe. Quantum gravimeters can detect minuscule changes in gravitational fields, revealing density variations. Neutrino observatories might capture particles released from nuclear interactions deep within lunar materials. Here's the groundbreaking possibility. A nuclear explosion might uncover voids or structures buried kilometers beneath the surface, features we've never been able to detect before. The lunar crust, averaging 50 kilometers thick, has only been studied through remote sensing and surface samples. A powerful blast could reveal chambers, lava tubes, or unexpected compositional boundaries that reshape our understanding of lunar formation. Some planetary scientists speculate that the moon contains vast networks of lava tubes large enough to house entire human settlements. A nuclear blast could collapse walls, separating these caverns, exposing their existence. Think about this. We've drilled a few meters into the moon. That's it. But a blast like this, it's like giving the moon an ultrasound, whether we like it or not. We've mapped the moon's surface in incredible detail, but what lies beneath remains largely mysterious. A nuclear explosion would violently pierce that veil of ignorance. Every seismic wave bouncing through lunar rock would carry information about what it passed through. Resource destruction. The moon's poles harbor a treasure more valuable than gold: water ice. Billions of years of comet impacts have deposited water molecules that remain frozen in permanently shadowed craters. If a nuclear explosion hits one of these polar regions, the intense heat would instantly vaporize this ancient ice, turning a crucial resource into radioactive steam that escapes into space forever. Scientists estimate that the moon's poles contained at least 600 million metric tons of water ice. This ice isn't just scientifically fascinating. It's literally rocket fuel when split into hydrogen and oxygen. Here's the shocking scenario. A single well-placed nuclear bomb could destroy enough water to fuel an entire Mars mission. NASA calculates that a crewed Mars mission requires roughly 200 tons of propellant, much of which could be produced from lunar ice. NASA's Artemis program has meticulously mapped these water ice deposits. The planned Artemis base camp depends on harvesting this ice for drinking water, oxygen, and fuel production. A nuclear detonation near one of these sites would irradiate the surrounding area, making it unusable for generations. The contamination wouldn't just be radioactive. The blast would mix the pure ice with lunar dust and vaporized bomb components, rendering it useless for the precise chemical processes needed for fuel production. Beyond the immediate destruction, radioactive isotopes would penetrate the remaining ice, requiring complex purification before human use. Some isotopes, like plutonium-239, remain dangerous for over 24,000 years. But while the scientific fallout is devastating, the public reaction might be even more explosive. The global freak out. The flash of a nuclear explosion on the moon would be visible to billions. Depending on the bomb's yield, it could appear as a sudden, star-like point or brilliant flare that outshines everything in the night sky except the moon itself. In our hyper-connected world, amateur astronomers continuously live-stream telescope views of the moon to thousands of viewers. Imagine the chaos when those feeds suddenly capture a blinding flash on the lunar surface. Within minutes, videos would flood social media. Moon explosion would trend globally. Confusion would reign as everyone asks the same question: what just happened? News networks would interrupt broadcasts with breaking alerts. Experts would be rushed onto air before they've had time to analyze what occurred. In the information vacuum, speculation would flourish. Was it an asteroid impact? A volcanic eruption on a supposedly dead world? A weapons test? Or something more sinister? Perhaps a message from another civilization? History shows how humanity reacts to unexplained cosmic events. When the Trinity test lit up the New Mexico sky in 1945, residents reported UFO sightings. The Starfish Prime nuclear test in 1962 created auroras visible across the Pacific, triggering panic about the end of the world. Even natural events caused mass confusion. The Tunguska explosion in 1908 flattened 80 million trees in Siberia, but left no crater. For decades, theories reigned from meteor strikes to alien spacecraft. Now multiply these reactions by our modern media environment. Conspiracy theories would spread faster than scientific explanations. Religious groups might declare it a sign of apocalypse. Markets could tumble as uncertainty grips the world. Government denials would only fuel suspicion. If no nation claims responsibility, the mystery deepens. If a country admits to detonating the bomb, international condemnation would be swift and severe. Imagine it. You're watching a moon livestream and suddenly, bam, a white-hot flash. What would you think just happened? Let us know in the comments before we reveal what's really going on. Would you assume it's a technical glitch? An asteroid impact? Something military? Or something we've never even considered? The first minutes after such an event would be pure chaos as humanity collectively tries to make sense of what they just witnessed. Back to Earth. Satellites at risk. The debris ejected from a lunar nuclear explosion wouldn't just disappear into the void. Some would follow predictable trajectories governed by orbital mechanics, and many of those paths intersect with Earth's orbital zones. Computer simulations show that up to 5% of lunar ejecta could eventually cross Earth's orbit. With thousands of satellites circling our planet, the risk of collision becomes a serious concern. The danger isn't just from large chunks. In space, size doesn't matter as much as velocity. A marble-sized piece of moon rock traveling at 11 kilometers per second carries the kinetic energy of a hand grenade. Even microfragments, lunar dust accelerated to cosmic speeds, could erode solar panels, damage optical equipment, or puncture pressurized modules on the International Space Station. The timing makes this particularly dangerous. We're in the midst of a satellite boom, with companies launching thousands of new units for global internet coverage and Earth observation. We've seen this scenario play out before. In 2007, China tested an anti-satellite weapon by destroying one of their own weather satellites. That single event created over 3,000 trackable debris fragments and thousands more too small to detect. 15 years later, the International Space Station still performs emergency maneuvers to avoid this debris. Some fragments will remain in orbit for centuries. A lunar nuclear explosion would be vastly more powerful, potentially creating a debris field that complicates space operations for decades. The fragments would follow more unpredictable paths than typical space junk, making them harder to track and avoid. With satellite networks controlling everything from military communications to financial transactions, the cascading effects could reach every corner of modern life. This isn't just about the moon. If one piece of debris crosses paths with a communications satellite, it's like punching a hole in global internet coverage. Think about how much we depend on satellites. GPS navigation, weather forecasting, television broadcasts all rely on delicate equipment orbiting Earth. These systems weren't designed to withstand impacts from hypervelocity lunar fragments. The most frightening part, we might not see it coming. Our space tracking systems are designed to monitor known objects in predictable orbits, not random fragments arriving from the moon on chaotic trajectories. Despite the catastrophic scenarios we've explored, this nuclear nightmare almost became reality during the height of the Cold War. In 1958, the U.S. Air Force developed Project A119, a classified plan to detonate a nuclear bomb on the moon. The motivation wasn't scientific curiosity, it was pure political theater. After the Soviet Union launched Sputnik, America desperately needed a dramatic display of technological might. What could be more visible than exploding a nuke on our nearest celestial neighbor? The plan called for a relatively small 1.7 kiloton device, the W-25 warhead, to be launched toward the moon's terminator line, where dark meets light. The flash would be visible to everyone on Earth's night side. A young astronomer named Carl Sagan, before his fame as a science communicator, worked on the project. His task? Calculate how the dust plume would behave in lunar gravity and how visible it would be from Earth. Meanwhile, Soviet scientists developed their own lunar nuclear plan, codenamed Project E-4. Like their American counterparts, they saw the moon as a cosmic billboard for announcing technological supremacy. Both nations eventually abandoned these plans. The practical challenges were immense. Early rockets were notoriously unreliable, and a failed launch would mean a nuclear warhead crashing back to Earth. But beyond the technical hurdles lay deeper concerns. Scientists recognized that contaminating the moon with radiation would destroy its scientific value. Military planners questioned whether the spectacle would inspire awe or horror. By the mid-1960s, humanity chose a different path. Instead of destruction, we pursued exploration. The 1967 Outer Space Treaty explicitly banned placing nuclear weapons in space or on celestial bodies. Just 2 years later, Neil Armstrong's footprint replaced the nuclear crater in our collective imagination. We chose to leave footprints, not scars. A nuclear bomb on the moon wouldn't destroy the Earth, but it would change everything we know about space, geopolitics, and even ourselves. The physical effects would ripple through our satellite networks, scientific understanding, and future space ambitions. The psychological impact might be even greater, forever altering how we view the night sky. That pale companion that has watched over humanity since our beginning would bear the mark of our most destructive technology. If you thought this was just another thought experiment, now you know better. A lunar nuclear explosion isn't just about physics. It's about cascading consequences we can barely predict. Hit subscribe, because next time we're diving into what would happen if the moon hit back. The cosmic balance we take for granted is more fragile than we realize. Every action in space creates reactions we must be prepared to face. Like, comment, and subscribe if you want more reality-bending science. And we'll see you in the next one. The Silent Witness. The moon has been our constant companion for 4.5 billion years. It has witnessed the entire human story unfold, from our first upright steps to our greatest technological achievements. If we were to scar its face with nuclear fire, that mark would remain for millions of years. No rain would wash it away. No wind would smooth its edges. The crater would outlast our civilizations, our species, perhaps even our planet as we know it. Long after the radiation faded, that scar would remain, a testament to a moment when we wielded godlike power, but failed to show godlike wisdom. The moon continues its silent orbit tonight, unmarred by our weapons. It reflects the same sunlight that has guided sailors, inspired poets, and marked our calendars since time immemorial. Let it remain that way, a pristine reminder that some boundaries should remain uncrossed, some experiments unperformed, and some powers unleashed only in our imagination.